here? What if I change the area this way? Less and less and less, and if I do this, basically I have zero flux, right? Because in this case, the area will point that way, while the magnetic field is tangent to it, so they make 90 degrees. So I hope it's clear what the area means. What the angle means. Because we have done it with the electric field, I'm just taking advantage of that. Okay? So hopefully we still remember. So the units will be, what are the units? Tesla times what?
Meters.
Area, which is meters squared. In the case of electric field, there was no special unit. It was again electric field units, newtons per coulomb times meters squared. In this case, they actually have a name for it. It's called the Weber. Yes. WB. Yes. So that's the magnetic flux. Okay. Now, let's talk about Faraday's law. Let's talk about Faraday's law. Well, before I talk about Faraday's law, let me talk about everything we know so far, and then discuss Faraday's law. Here's what we know. So far, what we know. We know this. E dot dA is equal to what? Q enclosed. Q enclosed over epsilon dot, right? This is Gauss's law. That's Gauss's law, right? There is another law, very similar to Gauss's law for electric fields. I would show you, I would write down Gauss's law for magnetic fields. It says this, Gauss's law for magnetic fields, B dot dA, Liam, you were asking earlier, this is a closed area, a closed surface. If it's a closed surface, it's going to be zero. So this is another law. So this law is complete, and this law is complete. Both of the Gauss's law for electric fields, but Gauss's law for magnetic fields. What this one says is, for electric fields, you can enclose a single positive charge and have an electric field just coming out from that surface, right? You can have net flux coming out from a surface, from a closed surface, I should say. In here, it says you can't have net flux coming out from a closed surface. If you have a closed surface, the flux that comes out must equal to the flux that goes in. So the net flux is always zero. Which means this, you simply cannot have just a north pole by itself where the flux just comes out, right? Where you have a magnetic flux just coming out and somehow just enclose the north by itself. That can't happen. You must have a south so that whenever you have a magnetic flux coming out, it must come back in. So the net flux is zero, always. So that's that one. So these two laws are actually complete. Here's what we're going to learn today. E dot ds, closed loop integral, it used to be zero. Well, so far it's zero, okay, what we know. It just says the electric field is conservative. The amount of work the electric field does over a closed path is always zero, okay? But this one is only true for electric fields that are due to the electrons, to charges, due to charges. Today, we're going to learn this will not be the case if we have a changing magnetic field. So this will be modified. So this one here, we will change. So I'll put a star next to it because it's going to be changed. Here is another one that we learned. B dot ds was equal to what? Mu naught I enclosed. Good. What's this law? That's Ampere's law. This is not complete either. So yeah, we just learned it, but it would be plus something. And that something is added by Maxwell. So it's going to be called Ampere-Maxwell law. So this one will need to be modified. This one we're going to modify it right now. Okay? So let's modify it. Now, it's a law. You can't prove it. You only do experiments to confirm it. So here is the change. It was added by Faraday. I'll write it with Greek. Minus the magnetic flux. In other words, it's minus ddt of E dot A open surface, right? It can't be closed because if it's closed, what do you get? It should be 0. So this is Faraday's law. And we're going to apply this. And this is the potential difference in a closed loop. It used to be 0, but it's no longer 0. There is a non-conservative field. And that non-conservative field comes from changing magnetic flux. So let's see how this, let's apply it to this case. Make sure we get everything that we have here. So let's just apply it to that particular case. More than half an hour. Here is the rod, right? And we're going to move the rod with velocity v. Let's say this distance this way is x, and we have our little resistor here. And this way, so it's a nice shape, it would be f. Okay? What's the area of this shape? X. And the magnetic field is going to be in. Okay? Magnetic field is going to be in. And our goal is to find the current. And we're going to apply Faraday's law to find the current in this circuit. We're not going to apply forces anymore. We use the forces. I'm going to show you how you can arrive at the same thing using Faraday's law. So Faraday's law says E dot ds closed loop. So that will be the potential difference across the resistance, right? The potential difference across the resistance. Another way, by the way, they call another way you can see this. It's called the EMF.
What is that?
The EMF. Instead of having a battery, by changing the magnetic flux, you're creating what acts like a battery.
Sorry, for the third equation, I don't get it why you have two equal signs.
This equal sign?
Yeah.
Oh, this equal sign. So up to here, is that okay? This is Faraday's law, right?
Oh, okay.
This is Faraday's law. So now minus ddt of the flux. So this is the flux. So that's the flux. This is flux. That's magnetic flux. Is the equal sign here? Okay. Anybody else? So let's first, we know the area. The area is, you said Lx, right? L times x. The flux is the magnetic field times the area, right? That's the magnitude of the flux. Isn't it? Now, it's an open surface, so is the area of this thing pointed towards you or into the page? We would worry about the convention later. I'm just caring about magnitudes for now. So the magnitude is just magnetic field times the area. I know the angle between them. If it points this way, what's the angle between the magnetic field and area? The area is this way, 180. So it would be minus BA, right? But if the area points in, what's the angle between them? 0, so it's going to be BA. So they will differ by a minus sign. I don't really care about the minus sign. We will fix that, okay? So it's just BA, okay? So that's B times L times X. That's B times L times X.
How is it going out into a median going into 0 if the area is perpendicular to
Yeah, so if the area points this way, in what direction is the magnetic field?
if they're perpendicular, you think the median or the median?
It's not that. I think you mean perpendicular to the border, the area.
Yeah.
But what angle does that area make with the magnetic field? Because the angle here is the angle the area makes with the magnetic field. So you make 180, right? Yeah. Okay, good. All right. So just to demonstrate, make sure we're good. So here is the. Imagine this is the area, and the magnetic field is going in, right? Magnetic field is just going in. So if I want it to be 90 degrees, then this would be 90. The magnetic field will just pass by, and you'll get 0 flux. Right? So, does the demonstration make it worse? No, made it better? Okay. Okay. All right, so what's the flux dP? B is constant, L is constant, so I have dx dt. So it would be B times L times dx dt. What's dx dt? That's V. Yeah. That's the rate of change of x, right? As you pull the rod, x will get larger and larger. Or if you push the rod, x will get smaller and smaller. At any rate, it's just, that's the speed of the rod. Now, this is the right side of Faraday's law, right? This is the right side. Again, ignore the minus sign. Don't worry about the minus sign. And that's equal to the EMF. It's like I'm connecting it to a battery that's providing me with this voltage. Like I'm connecting it to a battery that's providing me with this voltage. I'm going to dig deeper in a little bit with this Faraday's law. When we talk about what's called induced fields. And we don't have to calculate the induced field, but for now, this is the voltage. This is our EMF. Okay? That's the magnitude. Again, ignore the minus sign. Okay? Don't worry about the minus signs. We're going to find the current. So what's the current then? This, right? Does this match with the currents we got earlier? Yes. And so the power and everything else we match, right? Good. The only thing missing here, does Faraday's law tell you the direction of the current? At least the way we did it, no. But there are minus signs there on purpose. It tells you the direction of the current. So let's try to figure the direction of the current. There would be a current, and the current can either be clockwise or counterclockwise. The current in this circuit can be this way or this way. Those are the only two options. Its magnitude is this much. So now, in what direction is the current? Lenz's law, which is this minus sign, is called Lenz's law. This minus sign is due to Lenz. Lenz is a name, so Lenz.
The law is minus sign?
Yeah. Yeah, it's the minus sign. And it tells you the direction of the current, and also it would be the electric field also. So what does it say? I would say it in words, and then we will do several examples on how to calculate, on how to figure the direction. It just tells you the direction. It says the induced current, the current is induced current. I will write it. The induced current flows in a way to reduce the change in flux. To reduce the change in flux, or to oppose the change in flux, whatever the word you want to use. So that's how the current will flow. Okay, so now let's reason through. After you have written it, I want to reason through this and then predict the direction of the current. Okay? Yeah.
This is changing magnetic flux.
The induced current flows in a way to reduce the change in flux. Yeah, magnetic flux. Yeah. Yeah, in this context, only magnetic flux, right? No electric flux today. Okay, so let's look at this problem. So you're opening the gate. What's happening to the area as you move the slider or this rod?
Getting bigger.
The area gets bigger. So what's happening to the flux?
It's
It's bigger. There's more area available for the magnetic field to get through.
Yeah.
So the flux is getting bigger, right? So you have flux that's into the board and it's getting larger. We need to oppose it. We need to reduce it. Okay? So flux is in and getting larger. How do we oppose it? We need to produce some magnetic field that's out. Okay? So the current has to run in a way so that it will create some magnetic field out that will help reduce the change in flux. So that's the direction. So how should the current run in order to create a magnetic field that's this way?
Left, down, right. Right, down,
So up, like the counterclockwise.
counterclockwise.
So that makes sense, right? Because if the current is this way, so let's use our right hand. So if the current is this way, this is the current. What do? Your thumb in the direction of the current. So what's the direction of the magnetic field? Out. How about here? Out. Here. Out. All of them are out. Okay? So the current will run counterclockwise. Current will run in the counterclockwise direction. So I'm going to do several examples actually. Here's one. Basically all the possibilities in there. All right? I'm going to give you all the possibilities and then, yeah. Here's the first possibility. Let's say I have a loop, a current loop, or a rectangle. So it doesn't matter whether it's, the current will run clockwise or counterclockwise, right? Whether it's a circle or a rectangle or whatever. So let's say I have a magnetic field that's in, right? So the magnetic field is into the page, and B is increasing. So let's say the magnetic field is in and increasing. So the magnetic field is what? In and increasing. So what direction is the flux first of all? In, and it's getting larger, right? So we need to oppose it. So we need to create some magnetic field in what direction? In towards you, right? So the magnetic field that we need to introduce or induce would be this way. So the current should go in what direction? Counterclockwise. Yes. So the current should go counterclockwise. I hope that is clear. The current will need to go counterclockwise. Because if the current is counter, so again, just follow the current with your thumb, and the magnetic field will be out. So that opposes it. So the next possibility, there are three more. It's this one. Magnetic field is in, but decreasing. So the magnetic field is in, right? So you have flux into the board. The flux is into the board. Magnetic field is pouring into the board, but it's getting less. So we're losing flux, right? So we always want to oppose the change. We want to oppose the change. So we just want to keep it the same. That's the goal. So what happens? How should the current go?
Clockwise.
It should go clockwise, because when it goes clockwise, it helps create the magnetic field that's in, and it helps maintain the magnetic, the same magnetic flux. I'm not saying the flux will be the same when you induce the magnetic field, but it helps slow down the change. Okay? So next one is this. Now the magnetic field is out. Here's the magnetic field. It's coming out, but B is increasing. So the magnetic field is coming out, and it's getting larger. And so, what did he say? Will the current will be clockwise? Yes, the current will be clockwise. Why? Let's again, please, if you haven't thought about it, in the first two, please think about this. In what direction is the flux? Or in what direction is the magnetic field? It's towards you, right? And it's getting larger. We need to oppose that. To oppose it, we need to create some magnetic field that way. How do you create a magnetic field that way? By having a current that's clockwise. So the current needs to be in this direction. Because if the current is in that direction,
What's the point?
the final case, I think you guessed it, right? Is this, but B is what? Yeah. So in this case, what? Current could be counterclockwise. Hopefully my arrows are not going against each other. Are they the same? Yeah. Good. Yeah.
So what's the point of like making it to balance?
It's a law of nature.
Oh.
Yeah, that's like Faraday's law and Lenz's law. So that's the short answer. It is a law of nature. Here's the second answer. It's also another law of nature, which is conservation of energy. Imagine it worked opposite to this way. You gain flux, so the current will go to make the flux even larger. So what happens? So the flux gets even larger, and the current has to go even more, and the flux keeps getting larger and larger and larger. And so basically, you would just have a battery with no connection by itself, and that violates conservation of energy. I think I addressed it in the worksheet. So the short answer is it's a law of nature. The longer one is it has to, because it has to. Otherwise, conservation of energy would be violated also. Yeah.
Is this anything like friction?
Friction. Why? I don't think so. Maybe. I mean, I have to think about it. Yeah. Let me give you a fifth case. Here's the fifth case. Right? That's the loop. This is the magnetic field, but B is constant. In what direction should the current go? Yeah, no current. The flux is constant. There is no change, so there is nothing to oppose. So no current. Induced current is only there when there is a change. Okay? When there is a change. Now, how do you change the flux? How do you change the flux? There are different ways. The flux is this. Magnetic flux is B A cosine of theta, right? B A cosine of theta. How do we change the magnetic flux? I can make the magnetic field stronger or weaker, right? We can make the area bigger or smaller, like we did with the slider there, the rod. The more you pulled it, the area got larger. You can push the slider in, you can make the area smaller. Right? You can make the magnetic field, you can change B, you can change A, and you can change the orientation. You can change the direction of the area. Okay? The direction of the area, or the angle between the area and the magnetic field, I should say. So that's what you can do, and then you can have a change in flux. So for instance, for this one here, if you want to have a steady current, so if you want to generate electricity, right, you can do this until you get tired, right? Or imagine I have this magnet this way, and you attach it to like a wheel or like a fan, and you let the wind blow. What happens? You start to turn, and as it turns, as long as there is wind, there will be a current. So you can generate electricity using wind. That's one way.
What?
Yes. So if I turn this, I'm changing the angle between the magnet and the area. That's one way to generate. Another way, or another context, is to, for example, if you have your bike, there is a wheel, it turns, right? And the light has a little thing that touches the wheel. And then when you turn your wheel, you would spin something, and then the light turns on. Who is doing the work? You. You're the one spinning the wheel. And as long as you keep the wheel spinning, the light will keep going. You can have, again, like this one, wind, or you can have water falling, and when it falls, it circulates. It's one way, steam, whatever, and so you can generate electricity in this way. So, yeah.
Sorry. Where does it correlate with the magnetic field? Like, what's the connection with the?
I'm changing the angle, right?
Oh.
Yeah. So if I keep the magnetic field and the area the same, I mean, for example, this loop, I can't make the area bigger or smaller, right? But I can make the direction change. It's easier in our case to just spin the magnet than spin the area, but you can change the direction. So let me give an example for a similar one to this one. It's meant to be in 3D, so please bear with my drawings. So suppose I have a magnet here. Here's a magnet, like this. There are nicer pictures in the textbooks than this one, but here is a south, so there is a magnetic field this way, right? There will be a magnetic field from north to south. So what I do is you put a loop here, and the loop will look maybe like this, something perpendicular. And maybe I have a light bulb here, like here. And when I spin the loop, right? When I spin the loop, so I'm going to show you that flux, magnetic flux is equal to the magnetic field times the area times the cosine of the angle. What do I mean? If the area is this way, the magnetic flux will get through, right? How about this way? How much the flux?
No,
Zero. So the magnetic flux goes from something to zero, and then to something, to zero, to something, to zero. So as long as I'm spinning it, the flux is changing. Why is it changing? Because which one I'm changing here? Theta, right? Theta is changing. And if I'm spinning it at a constant rate, let's say it's my wheel in the car, maybe I'm cranking, like I have a little thing here that I can use to spin this, right? There is a way to connect it so you can spin it. So imagine I'm just spinning that loop, and from mechanics, the angular velocity times t, right? Omega t. So I'm spinning this at angular velocity omega. Angular velocity or angular frequency omega. Right? That's the flux. So the induced EMF is going to be d flux dt, or minus d flux dt. It's going to be v times a times omega times the sine of omega times t. The derivative of cosine is minus sine of omega times t. That's the induced EMF. So as long as you spin, there will be this. And if the light bulb has a resistance R, then the current right? The current would be actually an AC current, an alternating current. The reason is the current is sometimes positive, sometimes negative, because the sign is sometimes positive, sometimes negative, meaning the current doesn't just go clockwise or counterclockwise, it alternates. And so that's a generator. That's how you generate, in principle, how you get something that generates electricity.
Or like, if you store the energy that you put into a battery with the positive current,
Yeah.
then with the negative current, will it take energy from the batteries?
It depends. There are ways to keep it by having a current that flow only in one direction. Yeah, we do that. Which brings me to the following. Yeah, the average current is what? 0. Because the sine, what's the average of a sine over a cycle? Yeah, the sine is plus and then minus, right? So the average is 0. But what's the power? It's I squared R, right? So let's see. If you square this and multiply by R, you get B squared, A squared, omega squared over R, and then sine squared of omega t. Now this average is not 0. The average of sine squared is not 0. It's a half over a cycle. So the power is not 0, which makes sense. Once the light bulb shines, you can make it, when the current is negative, somehow capture that light back again. So the fact that the current runs one way or the other way through a light bulb, the light bulb doesn't care whether you connect it to the positive or the negative end of the battery. It will still consume energy. Okay? That's the importance of Faraday's law. Basically, everything modern, the modern economy, you wouldn't have electricity without it, right? You wouldn't have electricity. If you can't generate electricity, you basically can't have anything that you use every day. So that's Faraday's law. It runs everything modern, basically. Yeah. You got it. Okay. All right, so that's that. Now let's do a more theoretical thing than practical, which is the induced electric fields. We have been dealing here a magnet going through a loop, right? What if I'm in vacuum in outer space and I have a magnet, right? I'm far away. There are no loops around me, no conductors, anything. And somehow I wiggle this magnet back and forth or rotate it or something. So the magnetic field is changing in space, right? For example, this spot, when I move the magnet away, the magnetic field there gets weaker, right? If I bring it closer, the magnetic field gets stronger. Does anything happen?
No.
There will be no current because there are no conductors, there are no charges where the current would move, right? But would anything happen? What Faraday's law says would induce an electric field. So there would be actually an electric field induced by the changing magnetic field. So you don't need charges to generate an electric field. So charges are not the only source, not the only way to generate an electric field. If you have a changing magnetic field, you can induce an electric field. And the question is, how do we calculate it? So that's what we're going to do. So I'm going to erase the board. So you don't keep watching me erase and pause.
Professor, so you say that
Okay, so induced fields, induced electric field. Okay, induced electric field. So imagine, just to start, imagine you have a region in space where the magnetic field is into the page, but only confined to here. So imagine you have a magnetic field. This is not a loop, like a conducting loop or anything, but imagine we have a region in space of radius, let's say capital R, and we have magnetic field that's into the page everywhere, okay? And the magnetic field is B of E K hat minus. So imagine the magnetic field is in, and it's increasing, maybe decreasing with time. And it's into the page. So if there is a magnetic field and it's in, according to Faraday's law, there will be an induced electric field. So here is E dot ES minus E T of B dot A. So the question is, what's the electric field in this region, inside this region? And what's the electric field outside of this region? What's the electric field inside, and what's the electric on the outside of this region? So that's our goal. Okay? So we need to do these integrals, left side, right side, and the derivatives. So for this, we have to find a line integral, right? E dot ds. So we need to figure whether we're going to go, we need to find a closed loop, and we need to figure whether we're going to go clockwise or counterclockwise around the loop. Okay? We're going to go clockwise or counterclockwise around the loop. It's up to us. So we're going to choose one way. We're going to choose maybe, I usually prefer counterclockwise for some reason. So I'll just choose counterclockwise. Now, if we choose our loop to be counterclockwise, for the sake of integration, then the area, by your choice, if it's counterclockwise or clockwise, that will tell you the direction of the area. So the convention is this. Here's my loop. I'm going to choose a loop inside here, a loop of radius r, and I'm going to go around the loop counterclockwise. I'm not saying the current, there is a current and it's counterclockwise or anything. There is no current, because there is no actual physical loop. Okay? I'm going to go counterclockwise, and if you go counterclockwise, then according to the right-hand rule, the area, the convention is the area will be out. And here is the rule. If your loop is counterclockwise, the area will be out. That's the direction of the area. Counterclockwise, the area will be out. If you go clockwise, in what direction do you think the area is? It will be in, right? And I think you guys probably did this. It's the same convention in Stokes theorem, I think. The way you loop, it tells you the direction of the area. That is the convention. So the area in this case, let me write it down. The area is whatever the area of the loop is, right? This is the area.